Good morning. Today we'll see a little more about 2D sampling theorem. We have already seen the theory of 2D sampling. That is enough for explaining the sampling theory. And what we have to see here is how we can prove the sampling theorem. So there are two methods explained over here. First method involves a lot of equations. So I think it will be better to adopt the second method. So the second method, you are multiplying the analog image with two-dimensional comb function. So this is the two-dimensional comb function. Okay, all these are impulses, the x direction and y direction. And this is the three-dimensional view of the comb function. You can see all the impulses over here. Okay. So this will be the equation for the two-dimensional comb function. Equation for this image, that is comb of xy. The impulses are spaced with the spacing of delta x in the x direction and delta y in the y direction. So if you write the equation for this, it will be k equal to minus infinity to plus infinity, k2 equal to minus infinity to plus infinity, del of x minus k1 into delta x, y minus k2 into delta x. Okay, we have seen the theory for all these things. We have seen what a bed of nails function is. This is the bed of nails function. So whenever you are asked about the theory of 2D sampling, you have to mention this comb function and write this equation, draw this diagram. Okay, now you have to add the image also to this comb function. Then multiply this comb function with the image function. So analog image f of x comma y is multiplied by the comb function and you get f of m comma n. Okay, so this is a sample function of f of m comma n. So f of m comma n will be, this is the image function expressed in two dimension, f of k1 delta x, k2 delta y. And this is the delta function, del of x minus k1 into delta x, y minus k2 into delta y. Okay. So we know that convolution in spatial domain is equal to multiplication in frequency domain and vice versa. So for the purpose of analysis in frequency domain, we will take the Fourier transform of the input analog image and the 2D comb function. Let's take the Fourier transform of this one and this one. How will you write the Fourier transform of f of x comma y? It is just the analog image. So it will be given as f of omega 1 comma omega 2. And the Fourier transform of the comb function is given as comb of omega 1 omega 2. It is written as 1 by delta x, 1 by delta y. P equal to minus infinity to plus infinity, Q equal to minus infinity to plus infinity, del of omega 1 minus P by delta x. Since it is frequency domain, it is 1 by the time factor. So this is minus P by delta x. So same as this one, except that K1 and K2 are replaced by P and Q here. So this will be del of omega 1 minus P by delta x, omega 2 minus Q by delta y. So now you have the Fourier transform of f of x comma y and comb of omega 1 omega 2. Now the spectrum of the 2D comb function is convolved with the spectrum of the analog image, which is given by f of omega 1, omega 2, convolved with comb of omega 1, omega 2. So this is given as, this equal to should come on this side. F of omega 1, omega 2 is equal to f of omega 1, analog omega 1, omega 2 into comb of the Fourier transform of the comb function. Here again we are replacing this by its expansion. We are expanding it as k equal to minus infinity to plus infinity, L equal to minus infinity to plus infinity. So this will be f of omega 1 minus k, omega 2 minus L. And this will be summation of p equal to minus infinity to plus infinity, q equal to minus infinity to plus infinity, del of k minus p by delta x, L minus q by delta y. So just remember this equation. This is the most important equation. F of omega 1, omega 2, you are taking the Fourier transform of this one into Fourier transform of this one. So as summation is a linear operator, interchanging the order of summation. Interchanging all the order of summation, you are bringing all the summation terms here and multiplying these two terms. So Fourier transform of this one will be 1, delta function will be 1. And this occurs at k equal to p by delta x. So this one becomes 1 at k equal to p by delta x and L equal to q by delta y. So substitute k equal to p by delta x and q equal to and L equal to q by delta y in this equation, and this term becomes 1. So this will be your final expression. Expression for the sampled image. This is 2D sampling. So omega 1 minus p by delta x, omega 2 minus q by delta y. This will be your final expression. In the other method, which was explained initially before this, here also the equation, we arrive at the same equation over here. Del of x minus k1 into delta x, y minus k2 into delta y. Sorry, omega 1 minus 2 pi k1 by delta x, omega 2 minus 2 pi k2 by delta y. So in the method that we saw, this factor is replaced by p and this one is replaced by q. So for 2D sampling theorem, you should be able to explain this. And we have seen in detail the diagrammatic representations also. How the bandwidth would be. This is omega Sx. This will be the 2 omega x0 will be the bandwidth. And Nyquist criterion should be satisfied. Omega xs should be less than 2 omega x0. Or omega 2 x0 should be greater than this should be the reverse direction. This should be in the reverse direction. Omega xs should be greater than twice omega x0. Kindly note this change, and this is written correctly. Omega ys should be greater than 2 omega y0. Okay. So this distance should be greater than twice the bandwidth. Otherwise, what will happen? Twice the bandwidth. If this comes closer, both these things will overlap. 2 omega x naught difference, distance, spacing. This overlapping illada verulu. Otherwise, it will lead to aliasing effects. All these things are undersampling in the omega 1 direction, undersampling along the omega 2 direction. This is undersampling in both the omega 1 direction and omega 2 direction, both in the x direction as well as in the y direction. So image is to be sampled such that one can reconstruct the signal from its samples without errors. So find out f of x comma y. Expand this. Find out f of omega 1 comma omega 2. You have to find the values and plot it in the 2D space. If you're finding this difficult, there's no need to go after the problem. I don't think it is important for you. Okay. Okay, just be thorough with the theory behind this 2D convolution.